Again, welcome to lecture 10-1. Lecture 10-1. This is business calculus, mathematics 200, and our main topic today is relative maxima and also minima. And the concept of relative maxima and minima is using derivative to find the turning points of a graph, either increasing or decreasing. And we're going to explain in detail soon. Maxima means the turning will be up. So it's like we are going from increasing to decreasing. The minimum means down. So from decreasing to increasing. And we're going to discuss that soon. So again, our course textbook chapter 10, and this is 10-1. The topic again is a relative maxima and minima curve sketching. So we're going to find the relative maxima and also minima. Also the horizontal point of inflection of the functions. Also, we're going to learn how to sketch graphs of a function by using the information by the maxima, minima, and also the horizontal point of inflections. So the first thing we should know is that every graph, especially if we have a linear graph means the variable highest exponent is 1. There's no any turning point because the graph is straight. But when we have any type of graph, non-linear, it can be any type, parabola, exponential again, or most of the time we're going to get a turning point in the graph, either from increasing to decreasing or decreasing to increasing. So here we are saying that in addition to intercepts, we know what is an intercept, a graph maybe to intercept each other, or asymptotes. We can use the first derivative as an aid in graphing. The first derivative identifies the turning point of a graph, which helps us to determine the general shape of the graph. And we will soon see an example. So for example, given here, if I have a quadratic equation ax squared plus bs plus c, the first derivative or the derivative of f at x will be 2ax plus b. So we get 2as plus b equal to 0. So we can find the x to be minus b over 2a. This will be the solution of the x coordinate of the vectors, which is the turning point of f at x. If we remember quadratic equation pre-calculus, if I have f at x equal to ax squared plus bs plus b, this is a parabola quadratic. We can find the turning point on this. Again, we can say whether the parabola will open upward or downward would depends on the a value here. So if a is either positive or negative, then either it will open upward or downward. So we can find the turning point using different method. Find the first derivative of the function, then find the x, which will be minus b over 2a. If you remember, there was the same formula for finding the vectors for a quadratic function. So this is an example given again. Here we have y equal to 1/3 s cubed minus s squared minus 3s plus 2. So if I plot this graph, this is what we get. This is our graph. Now you can see that when we plot this graph, we have a 2 turning points. We have -1 and 11/3. And this will be called the relative maximum. So we can see that the turning point is from increasing, the graph is increasing, to decreasing, increasing to decreasing. And that will give us the relative maximum or relative mass. Again, you follow my cursor on the screen. We can see that this graph is increasing, then it turned, when it turned, it went down, decreasing. Now, in the relative minimum or minima, which is mean, we can see that we go from decreasing to increasing. So in this graph, we have a 2 turning points, the relative mass and also the relative mean. The relative mean will be 3 and -7, and the relative mass will be -1, 11/3. Now in this chapter, our goal is how do we find these 2 points without plotting the graph? I mean, plotting the graph, we can see and we can get it straightforward from the sketch. And that's our topic today. So first thing we're going to do is get the definition of what is a relative maxima and what is a relative minima. So here we say, for example, if I have a point, 2 points, x1 and f at x1. This again, so we have a point. A point always have 2 coordinates. Here we are doing with 2 dimensions, the x and y points. So s1, f at s1 is a relative maximal point of the function f if only there is an interval around x1 on which f at s1 is greater than or equal to f at s2 for all x in the interval. So in this case, we say that the relative maximum occurs at s equal to x1, and the relative maximum is f at x1. So the condition given to here is that it will be relative maximal point if the point that we have s1 and f at s1 is greater than f at x in all the interval period. What we mean here, we can see we have an interval, I'll say from here on my cursor all the way down. So we can say, okay, from here to here, we are having the relative maximum and the interval from increasing to decreasing. And from this interval to this interval, we have decreasing minima. So that's the, again, we'll see more example. So the second point, S2, f at S2, is a relative minimum point of a function f if there's an interval from S2, around S2, in which f at S2 is always less than or equal to f at S. So it will be down. This case, the S2 should be less than or equal to f at x. And that is the whole concept. So here we say a function is increasing on an interval if the values of the function increase as the s value also increase. That is, if a graph rises as we move from left to right. Similarly, a function is decreasing on an interval if the values of the function decrease as the s value increases. Now, what we mean, let's go back to the graph here. You can see that from this point on my cursor, let's say here we have -1 to -2. We have an increase in y because as the graph increasing, what happened? X also is increasing. So s is increasing from let's say -2 to -1. But within that period also, the function is increasing. But when we start from -1 all the way to somewhere 3 here, we can see that the function is decreasing. Because as the function is decreasing, what happened? S also is increasing. So this means we have a decreasing function from -1 here all the way to here, 3. But from the 3 up going, so from 3 to, let's say this is 5, we have an increasing because 3 to 5 is increasing and also the function is increasing. So that's the whole concept. You can see increasing up to here, and this is the turning point at -1, decreasing all the way down as s is still increasing. When we say s increasing, we mean the x-axis. And also from 3 to 5, we can see that the function start to increase, while s also is increasing. So it's increasing interval. So we can see from 3 to 5, it's increase, function is increasing. But from -1 to 3, the function is decreasing. And from -2 to -1, the function is also increasing. And that's what we mean by this section. The function is increasing on an interval if the values of the function increase as what? S value also is increasing. So if the function is increasing and s is increasing, we say the function is increasing. But if the function is decreasing, but the s value is increasing, then we say the function is decreasing. So increasing and decreasing function, we say if f is a function that is differentiable on an interval between a and b, then the derivative of f at x greater than 0 for all x in AB, we mean that the function is increasing. The first derivative of f at x, if it's less than 0 for all the x between the interval a and b, if it's less than 0, then the function is decreasing. So we have a function f at x. We take the first derivative of the function, and if the solution is greater than 0, then we say the function is increasing. If it's less than 0, we say the function is increasing. Considering the interval here, the interval is between a and b. So here we have the same function again. We can see that in this function here, we have the same function we did before. We have two turning points, the relative maximum and the relative minimum. And this is the original function. Now, if I take the derivative of this function, I'll get 3 times 1/3. 3 minus 1 is 2. So I'll get 3 will cancel 3. So I'll get x squared minus 2x minus 3. And that's what we have here. The y derivative will give me s squared minus 2s minus 3. Now, if I plot this, this is what I will get. So here we are getting only the relative minimum, which is at 1 and -4. S is 1 and y is -4. That's our turning point, relative min. The reason why we say relative minimum is because it's decreasing to increasing. From increasing to decreasing is relative maximum. Increasing to decreasing. So here we say the figure 10.A shows the graph of a function. The figure 10.1b shows the graph of its derivative. So this is the graph of the original function. When we take the first derivative, this is what we get. Now the figure shows that the graph of y equal to f at s is increasing for the same values for which the graph of y derivative equal to f at s is above the x-axis. When what? The f at s derivative is greater than 0. Again, we're going to solve more example on this. Similarly, the graph of y equal to f at s is decreasing for the same x values. That is, when you look at the graph between -1 to 3, you can see that it's decreasing, which is right here, -1 to 3. And when you look here, also the same thing, -1 to 3 is decreasing. And that's what we are trying to explain here. Despite that the original function have 2 turning points, the derivative of it have 1 turning point, but the interval where they were decreasing is the same interval, for which the graph of is below the x-axis when what? F at s derivative is less than 0. So here we say the derivative of f at s can change signs only at values of x at which the derivative of f at s equal to 0, or what? The derivative of f at s is undefined. And normally we call this the critical values. So the critical value or the critical point is where we have the turning point of the function. Because the curve changes from increasing to decreasing at a relative maximum and from decreasing to increase at the relative minimum, we have the following. If f has a relative maximum or relative minimum at s equal to x0, then the derivative of x0 equal to 0, or the derivative of f at x0 is undefined. And this will give us again the critical values. Again, to understand this more, we're going to solve an example. And I will go through the example right now. So first thing also we should know is that when we are getting the interval, we should know that from increasing section, we assume is positive. Decreasing is negative. Increasing is positive. Decreasing negative. And remember, from the theory, we said that if f at a derivative of f at s is greater than 0, then it's increasing, so it's positive. If it's less than 0, then it's decreasing, which will be our negative. And that's the whole concept here. So we can see here, derivative of f at s1 equal to 0, horizontal. When it's less than 0, decreasing. Greater than 0 is increasing. That's our critical point. And this is for relative maximum. So from increasing to decreasing, we have relative maximum. Relative minimum, we say what? From decreasing to increasing. So we can say f at x derivative is less than 0. Derivative of f at s greater than 0, increasing. So from decreasing to increasing, we have relative minimum. The same thing here. From, again, decreasing to increasing, we have relative minimum. From increasing to decreasing, we have relative maximum. So those are the two things for this topic. How do we find the relative maximum and relative minimum without plotting the graph? And that's the next step now. So on the left side, we have the step, and the second, on the right side, we have an example. So if you want to find the relative maximum or minima of a function, first, we just said it, we have to take the first derivative of the function. Now, when I take the first derivative of the function, I will equate it to 0. And that's what will give us the critical value. So find the first derivative of the function, set the derivative equal to 0, and solve for the values of x. And these are called the critical values. So first, find the derivative of the function, set the derivative of the function to 0, then find the value of s, which we call the critical values. The critical values is where we're going to have the turning point. Then step 3, substitute the critical values into the original function to find the critical points. Now the critical value, when we substitute to the original function, if we get a value less than a negative value, it means what? Decreasing. A positive value means increasing. 0 means horizontal. So now we evaluate derivative of f at x at the value of x to the left and 1 to the right of each critical point to develop the sign diagram. So we say that if it's the derivative of f at s greater than 0 to the left, and then the derivative of f at s to the right of then we have a what? A maxima. Remember, a maximum point means what? From increasing to decreasing. So if from my left, the derivative of f at s is greater than 0, it means it's increasing. To the right, it's less than 0, means it's going down. And then the opposite way will be the relative minimum. If it's less, the derivative of f at s is less than 0 to the left and greater than 0 to the right, then we have relative minimum. Now, let's go back to this is the whole concept here. We can see derivative of f at s greater than 0 to the left, derivative of f at s less than 0 to the right. So this is called relative maximum. Then derivative of f at s less than 0 to the left, derivative of f at s greater than 0 to the right, we have relative minimum. And that's what we mean in step 4. Now we are going to use information from the sign diagram and select the points to sketch the graph. Now let's see an example here. So here, the same question we had previously, 1/3 s cubed minus s squared minus 3s plus 2. So the first thing I'll do is what? Take the first derivative. So the derivative of f at s will give me s squared minus 2x minus 3. Then I will equate it to 0. Then I'll find the value of x. So when I equate it to 0, I was able to factorize this. This is a trinomial. So we know -3 and +1. When you multiply, you get -3. When you combine, you get -2. So we get +1 and -3. So this means s value will be s plus 1 equal to 0. We give s equal to -1. S minus 3 equal to 0. So the second S value will be 3. Now we have two S values. Now these are called the critical values. And there are no values of S make it have a derivative undefined. We said to find the critical value, we have two conditions. Equate the derivative of f at s equal to 0 to look for the value of x, and also the derivative of f at x equal to undefined to find. Normally, undefined means the equation we have square root. Square root of a negative value is undefined. Or the equation we have a denominator, any value divided by 0 is undefined. So there we can get the undefined condition also. Okay, so now we know the 2 points now. -1 and 3, those are our only critical values we have too. So let's plug -1 to the original function. We get 11 by 3. Then we plot also the 3. We get -7. So remember, when we plot the graph, this time we are not plotting the graph, but we get our points now. The first point is -1 and 11 by 3. Let me go back to the graph for a second, then we continue. You remember when we plot this graph, they didn't teach us how to find the critical values, etc. But from the graph, we can see that relative maximum is -1 and 11 by 3. Relative minimum is 3, -7. And this is what we look for, those 2 points. And from the graph here, that's what we just did. First, I have the equation, original function. I find the first derivative. After that, I equate it to 0. Then I find the values of x. I only get 2 s values because this function cannot be undefined. It's always defined. Then I'll plot those 2 values of x into the original equation, and I get my y position. So I get -1 will give me 11 by 7. 2, 3 will give me -7. So I get the 2 points from the graph, 3 and -7, and -1 and 11 by 3, which are here. And this is what I'm looking for. But now, when we plot the graph, I saw that -1, 11 by 3 is maxima, relative maxima, because it's from increasing to decreasing. But since we are not plotting the graph, now we have to test these points to see whether it's relative maximum or minimum. So what we do, take any value between, here we are using -1. So take any value. Here they decided to use -2. Since I have -1 here, I can take any value between, let's say, -infinity to -1, right before -1. So I think the closest value I'll take you can use -3, -4, any value, but it shouldn't be up to -1. You are taking the interval from -infinity to -1, the x. So they decided to use -2. So when we plot the -2 to the first derivative, we get 5. Okay, 5 is greater than 0. So that means we have increasing. Okay, so the next we look at the value here. We have from -1 to 3. So I'll take 0. Take actually, this is what is plotted here. See, we have -1 and 3. So we want to know the turning points. So take any, let's assume the end here is negative infinity, here is positive infinity, the two ends, increasing and decreasing area. So we decided to use -2 here, and we get positive, so it's increasing. Now from 0 to 3, you can use 1, 2. Here they decided to use, let's see, where is it? They decided to use 0. 0 is better because it's more quick. Or you can use 1, 2. Make sure we don't use 3, so the interval somewhere here. So we use 0. When we use 0, the answer becomes less than 0. It's a negative answer. And we can plot it and see. See, when I put 0 here, put 0 here, I'll get -3. So if it's less than 0, so that will be decreasing, negative throughout. Then the last interval will be from 3 to infinity. So use 4. And here, let's see, they also use 4. 4, the answer is 5, so it's greater than 0, so positive, so it's increasing. So from here, we'll see that I have, okay, from increasing to decreasing. So this will give me relative maxima, the first interval. Then from decreasing to increasing, that will give me minima. And then that's it. So how do we find it? Again, when you plot a graph, you see it on a graph. So there's no need to go through all this step. But normally, this is how we find the relative maximum and minimum. One more time, we have an equation. Find the first derivative of the equation. Then find the critical value. The critical value means the first derivative of the equation, equate it to 0 and find the s values. Also equate it to undefined. By here, we have, for example, if I have s squared minus 2s, let's say s squared, this is the original graph, 1/3 s cubed minus s squared minus 3s plus 2 divided by s squared minus 1. Then I may likely get undefined of the function. Undefined, this function will be if s squared minus 1, let's use s squared minus, let's say, 4. So if it's s equal to 2, then I'll get what? 4 minus 4. That's undefined. We can't divide the numerator by a 0. Or let's say if I have s squared minus 2 again, let's say if I have any value that will make the 2 again 0. So here is very straightforward. We only have the critical values, condition of equal to 0, because whatever value we have for x, we always get an answer. It can never be. Normally, an equation can be undefined if we have a radical sign, a square root, or dividing a value by the denominator. If the denominator is 0, we have problem, undefined. Or if the radical value is negative or square root is negative, then we have. So after that, the answer we get after we equate the first derivative to 0 will be the critical values. And here we get two values, which is -1 and 3. Now go and substitute this value to the original equation, not the derivative, the first derivative, no, the original equation. And that will give us the f at x values, the y values. And that's what we get, 11/3. So we finish. Now we have the 2 points now, -1, 11/3, 3, 11/7 from the equation. But now we want to determine which one is relative maxima, which means from increasing to decreasing, and which one is relative minimum, which means decreasing to increasing. That's where we start at step 4 to test it. So we said in the condition that if the first derivative at x is greater than 0, then it's positive, increasing. If it's less than 0, then it's a negative, decreasing. But we have to use the interval. Remember in our condition, we say whereby the interval is between a and b. Here, our interval is here, 3 and -7. But we're also going to have, so we have 3 and -7 are y values. So the intervals will be -1 and then 3. Those are the critical values, -1 and 3. This is the points, the 2 points. So we have -1 and 3. Take any value before -1 to get the first interval. And we saw that, and we have to plug that value to the, again, the derivative. So that's what we get here. We use -2. Then we take the first derivative also. Between -1 to 3, we can use 0. So they use 0. Or you can use 2. It's up to you. 1, you can also use 1. But don't use 3 because the 3 is the end point. The end point. Then here we can use 4, 5, any value. We decided to use 4. We saw that the derivative of f at 4 is 5, which means it's positive. Derivative at f2, which is here, is -3, so it's less than 0, so it's negative. Then here we use 0. That's positive. We have -1 here, so we use -2. We get 5. Here we use 0, and here we use 4. So we saw the values positive, so we can get the relative maximum from decreasing to increase relative minimum. So that's the concept here: increasing, decreasing, and increasing. And that's the points that we find. So relative maximum, and the down again is relative minimum. So with this concept, again, we can sketch. If we know these 2 points, we know where the turning points are, increasing and decreasing. Again, we can sketch our graph based on those 2 points. Here they say we should find the relative maximum, minimum, and horizontal point of inflection. So this is a very good example. And then we sketch its graph. So we have h at x is equal to 1/4 x to the power 4 minus 2/3 x cubed minus 2x squared plus 8x plus 4. Again, this example will wrap everything that we are covering in this lecture. So we should pay attention. This is the last example. So in this lecture, we learn how to find the maximum value, minimum, and horizontal points of inflection. So as we said earlier, what is the first thing we should do? Find the first derivative of h at x. And that will give us 4 by 4 will cancel. 4 minus 1 is 3. So we get s cubed, and then 3 is 6. So that will give us 2s squared minus 4x plus 8 plus 0. So let's go. So that's what we have here. S cubed minus 2s squared minus 4s plus 8. So that's our first derivative. Again, we already covered in chapter 9 all the derivative rules. So here we apply the sum, power, and difference rules. Now, if I get the first derivative, what's the next step? I need the critical values. So I'm going to equate this equation to 0 and find x. Undefined, we are lucky we don't need undefined here. We don't have any denominator or square root. So let's equate it to 0. When we equate it to 0, we factorize our equation. Here we factorize by grouping. Again, this is pre-calculus. We divide the equation into 2. S squared is common here, so we get s squared s minus 2. Here 4 is common, and we get x also minus 4. So we get x minus 2 also. So that's what we have here. So finally, we get s squared minus 4 times s minus 2, and that's what we have here. Then we are looking for s. So our first s value will be 2. S minus 2 equal to 0 will give us 2. And here also we have difference of 2 squared. S squared minus 2 squared is 4. So we get s plus 2, s minus 2 again. So our answer will be either negative 2 or positive 2. So this is again our critical values. After we get this critical value, we are going to plug it into the original function so that we get a y point. Now we have the s point where it's turning, the graph will turn. But we need the y also to get the point. So the critical points are negative 2, negative 32 by 3, 2, 32 by 3, positive. Again, the steps is not showing here, but what we need to do is that plug negative 2 into the original function here, plot positive 2 into the original function, and this is what we get, negative 3, 2. So now we have our turning points. I would say we finish here, but the reason why we have to continue, this graph gave us only 2 points. We can see the 2 turning points, 2 turning points. We can see it here. But is the first one the maximum or is the second one minimum? I don't know. So we want to know which one is relative maximum, which one is relative minimum. So because of that, we have to start testing. Now the testing means we have to use the first derivative. If the first derivative of f at x is greater than 0, then we have increasing. If it's less than 0, we have decreasing. Again, we are not using the original function. We are using the derivative of the function. Then we know that from increasing to decreasing, we have relative maximum. From decreasing to increasing, we have relative minimum. And that's the next step here. So since this is my interval negative 2 to 3, I think I can use negative 3 or negative 4, negative 5. From negative infinity to negative 2. And always try to use the smallest value. So the next smallest value to -2 will be -3. So we decided to test with -3. Then from -2 to 0, I can use 1, but let's use the smallest value. I'll use 0. 0 is easy, so they decided to use 0. Then from 2 to positive infinity, they decided to use 3. So when you use -3, 0, and 3 to test the first derivative, which is 8h at x, the first derivative, this is what we get. And derivative of h at x, when s is -3, we get less than 0, so it's negative. When it's 0, positive. When it's 3 again, positive. So this means we have only one turning point. From decreasing to increasing, we have relative minimum, but we don't have no relative maximum because at this turning point, 0 and 3, both are increasing. So this is how the graph, actually when we plot the graph, this is how it looks like. So you can see that we have relative minimum, but when we reach here, the turning point, we have horizontal, then still increase. So we don't have no relative maximum here. It still went up. And this is not a relative minimum. Relative minimum means from decreasing to increasing. But here from increasing to increasing, then we have the horizontal. So that will be our solution. Now the next example here, they say the weekly sales S of a product during advertising campaign are given by the following, where T is the number of weeks since the beginning of the campaign and X is in thousands of dollars. Over what intervals are the sales increasing? So our goal here, we want to see where the interval where it's increasing or decreasing, which is T. T is between 0 to 20. Then what are the maximum weekly sales? Then next we sketch. So first thing we have to do is to find the first derivative of this function. Then we find the critical value. We equate the first derivative of this function equal to 0, then we find the value of t. Maybe we'll get more than one t, so we have 2t squared here. Then when we get the value of t, we substitute it to the original function so that we get the point. The point may have t and s value. Then when we get the point finish, we know the interval now. So we take any value between the interval and plug it to the first derivative. Then when we get a point, it means we know the turning point. But now we want to know which one is the relative maximum, relative minimum. But here the question says what's the interval where the sales increasing. So the first derivative, I plug the value in. If it's greater than 0, then it's increasing. If it's less than 0, then decreasing. Then the second section, we do the maximum. So let's go through the solution. So we find the first, this is again quotient. We know the quotient rule. Find the derivative of 100t, which is 100, multiplied by t squared plus 1, minus the derivative of t squared plus 1, which will give me 2t, multiplied by 100t, all divided by t squared plus 100 all squared. And that's what we have here. We can simplify the equation to reduce it down. Now we have to say the critical value, so we set it to 0. So when we set this equation to 0, this is what we get. And then we solve for the value of t. We get 2t value -10, +10. I'm not going through this because this is pre-calculus. For example, if I have this equation here, when I set it to equal to 0, I cross multiply t squared plus 100 all squared multiplied by 0 give me 0. So automatically I'll get 10,000 minus 100t squared equal to 0. And that's what we have here. Then 100 is common, so we take the 100 out, then we get 100 minus t squared. So 100 also will go away because 0 divided by 100 is 0. And that's why this 100. Then 100 minus t squared is difference of two squares. It will be 10 squared minus t squared, which will give me 10 plus t multiplied by 10 minus t. So 10 plus t equal to 0 will give me negative 10. 10 minus t equal to 0 will give me positive 10. So now we know this. We have to plot this to the original equation to find the point. Then after that, we know the point is 10 and negative 10. So we test it from left to right. 10 equal to 0 give the following sign. So when I plug this 10 into the first derivative, s at t, which is, again, let's go back one more time. This is my equation. I plug the value in, the testing value, and this is the sign it gave me, positive and also the negative. So this means we have increasing between 0 to 10 and decreasing from 0 to 20. Remember, I'm not using infinity here. Why I'm not using infinity? Because when you look at the question, they gave us the interval. Let's go back to the yeah. So they say the weekly sales S of a product during advertising campaign are given by what? The interval is from 0 to 20. So because it's from 0 to 20, again, the interval, if the interval is not given, then I'll assume it from negative infinity to positive infinity. So I'm going to use both negative 10 and positive 10. But in this case, I cannot use negative 10 because the interval is given to me in the question. The question said the t is between 0 to 20. So that's why when we reach here, we didn't follow the same step as the previous. See here, I'm not using the negative t equal to negative 10. No, we don't need to use it because the interval given to us was 0 to 20 by the question. If the question didn't give me interval and I use negative infinity to positive infinity, then I'll have negative 10 and positive 10 inside. But again, this is from 0 to 20. So I can only use the 10. And when I use the 10 to the first derivative of the equation here, if I plug in 10 here, when we solve this 100 times 10 squared, we get positive. We get positive. Take any value between, let's say I use 9. Or the best value to use, I will say, actually, I'll use 1. Again, you can use 9, it's up to you. So I'll use 1 here and I'll use 11. 1 and 11. So we get negative value for the first derivative because it's less than 0 and greater than 0. If I use any value between 1 to 9 here, my answer will be positive. So this means the increasing interval will be from 0 to 10, decreasing from 10 to 0, which is, hence increasing interval is from 0 to 10, right before 10, and then from 10 to up to 20. That's for A. Now B said we should find the, let's go back to the question again. B said, what are the maximum weekly sales? Then the last step is to sketch. So the maximum weekly sales, because S is increasing to the left of t equal to 10 and S is decreasing to the right of t, the maximum value will occur when at what? 10 t equal to 10. Why? Remember what we said earlier, relative maximum from increasing to decreasing. So here we have relative maximum. If it's decreasing to increase, we have relative minimum. So in this interval, we cannot find the minimum cells, only the maximum. So we plug in the 10 because that's the relative maximum point. Then we solve it, we get 5,000. Then we can plot our graph. So again, this will be the conclusion of relative maximum and relative minimum. Again, I'm going to make another video whereby I will be solving a problem on the board, and which will be similar to the homework assignment also. So thank you very much for this short video. If you want to comment it or like it, and that's fine. Also, you can subscribe it. Thank you.